Hey everyone, and welcome back. So, in our last few explainers, we've talked about how to turn AC into DC and how to change one DC voltage into another. Well, today we're tackling the final and maybe the most crucial piece of that puzzle, the inverter. This is the magic box that lets your EV's battery run its motor, and it's how solar panels can push power back into the grid. It is the absolute key to turning DC power back into the AC power that, let's face it, runs our entire world.
Okay, so here's our game plan for this deep dive. We're going to start with the absolute basics, the fundamental building block of any inverter. Then we'll look at the simplest but also the most problematic waveform we can make. After that, we'll pull out a powerful math tool to see exactly what's wrong with it, explore a really clever fix, and then, this is the exciting part, we'll unveil the modern, elegant solution that's used pretty much everywhere today. And to wrap it all up, we'll see how all these ideas scale up for some serious industrial power.
All right, first things first. Before we get into any of the fancy control stuff, we have to get our heads around the core challenge. How on earth do you make a current that flows back and forth when your power source, like a battery, only wants to flow in one direction? So let's look at that core problem and the clever bit of engineering that makes it all possible.
So this really is the big question, isn't it? You've got this steady, one-way stream of electricity coming from a battery, a solar panel, whatever it is. But the goal is to create that oscillating, back-and-forth flow of alternating current that powers, everything from your kitchen blender to giant factory motors. This is the fundamental problem that the inverter was invented to solve.
And here's the official definition. At its heart, an inverter is a translator. It speaks both the language of DC power, from our batteries and renewables, and the language of AC power, which is what our grid and most of our machines understand. And this translation job is absolutely essential for so many technologies we rely on every day. Things like adjustable speed motor drives, the uninterruptible power supplies that save our data when the power flickers, and, most importantly, for connecting green energy sources into the grid.
So how is this translation actually done? Well, the workhorse behind it all is a circuit called a full bridge converter. But you'll almost always hear it called an H-bridge, and that's just because if you look at a diagram of it, it looks exactly like a capital letter H. It's built around a really clever arrangement of 4 electronic switches. Now, these aren't the light switches on your wall. These are incredibly fast, powerful transistors that can flick on and off thousands or even tens of thousands of times every single second.
Okay, let's actually follow the electricity to see how this works. It's really just about directing traffic. So for the first half of the cycle, we close 2 switches diagonally across from each other. The top left one, S1, and the bottom right one, S2. The current flows out of the positive side of our DC source, goes through S1, flows across our load from left to right, and then goes through S2 to get back to the negative side. This gives us a positive voltage across the load. Simple enough? Now, for the other half, we open those 2 switches and close the other diagonal pair, the bottom left, S4, and the top right, S3. This time, the current flows through S4, goes across the load in the opposite direction, from right to left, and returns through S3. Now we have a negative voltage. And just by flipping back and forth between these 2 states, we've done it. We've created an alternating current.
Now here is an absolutely critical safety point. What would happen if, by mistake, we closed S1 and S4 at the same time? Well, you'd create a direct path with almost no resistance from the positive terminal of your DC source straight to the negative terminal. That's a dead short. It's called a shoot-through fault, and the massive rush of current would instantly vaporize your expensive switches. So to prevent this disaster, engineers program in a tiny delay called a blanking time. It's a brief moment where all the switches are off, ensuring that one pair is definitely off before the other pair is allowed to turn on. It's a simple but life-saving feature.
Okay, so we've got our basic tool, the H-bridge. So what happens when we use it in the simplest way we can think of? Well, this gives us our very first, most basic AC waveform. But as you're about to see, this simple brute force method creates a whole new world of problems for us.
So if we just program our H-bridge to flip-flop, going from the positive state to the negative state and back again, say 60 times every second, we get this waveform, a perfect square wave. Now, technically, this is alternating current. It spends half its time positive and half its time negative. But it's a very crude, very aggressive form of AC. And this quote right here just hits the nail on the head. You see, the AC power that comes out of your wall outlet is a nice, smooth, gentle sine wave.
A square wave is the opposite. It's jagged, it's abrupt, it's full of these unwanted extra frequencies called harmonics. The best way to think about them is as a form of electrical pollution or noise that's piggybacking on the main signal you actually want. And this noise is bad news. It's what makes motors buzz and vibrate, run hot, and waste a ton of energy.
So, to really get a handle on this harmonic problem, to see them, to measure them, and ultimately to get rid of them, we need to bring in a really powerful diagnostic tool from the world of mathematics.
And that tool is called the Fourier series. You can think of it as a prism, but for electrical waves. Just like a glass prism can take a beam of white light and split it into all its component colors, red, green, blue, and so on, the Fourier series can take any repeating waveform, no matter how jagged or complex, and break it down into a simple recipe of pure individual sine waves. It shows us the main ingredient we want, the fundamental frequency, and all the extra stuff we don't, which are the harmonics.
Now this is what's so cool about it. When we run our ugly square wave through this process, we get its unique harmonic fingerprint. And this chart shows us exactly what's inside. You see that first really tall bar? That's the main frequency we actually want, our fundamental, let's say 60 Hertz. But look what else is in there. There's a big chunk of the third harmonic, which is a sine wave at 3 times the frequency, 180 Hertz. And then there's the fifth harmonic at 300 Hertz, the seventh at 420 Hertz, and on and on. It turns out that a perfect square wave is mathematically built from the fundamental plus all the odd-numbered harmonics, with their size getting smaller as the frequency goes up.
And the beauty of this is that it's not just a nice visual, it's mathematically precise. This formula lets us calculate the exact voltage of any harmonic we want. Vn is the voltage of the harmonic, VDC is our input voltage, and N is just the harmonic number. 1 for the fundamental, 3 for the third, and so on. So if we plug in N equals 1 for our main frequency, we find that the peak AC voltage we get is about 1.27 times our input DC voltage. Then, for the third harmonic, its voltage is just 1/3 of that. The fifth is 1/5 of that, and so on. It gives us a completely predictable recipe for our messy waveform.
Okay, so now we can actually see the problem, and we can measure it precisely. So, let's look at the first really clever method that engineers came up with to start cleaning up this waveform. And, as a bonus, it also gave them a way to control its power.
The solution is actually quite simple in concept. Instead of just slamming the voltage from positive all the way to negative, we introduce a short controlled pause right in the middle of each half cycle. During this pause, the switches are configured in a way that the output voltage is forced to 0 for a brief moment. This creates a little step in our waveform, and we call the result a modified square wave, or sometimes a quasi-square wave.
Now, the effect this little zero voltage gap has on our math is incredible. It adds a brand new term to our harmonic formula, that cosine of n times alpha part you see there, where alpha is directly related to how long we make that pause. This new term is like adding a brand new, powerful control knob to our machine. So let's see what happens when we start turning that new knob. Let's say we very carefully time our zero voltage gap so that this angle alpha works out to be exactly 30 degrees.
And here is where the magic happens. Let's look at what our formula says for that really big problematic third harmonic, where n equals 3. That new cosine term becomes the cosine of 3 times 30 degrees, which is the cosine of 90 degrees. And if you remember your high school math, the cosine of 90 degrees is exactly 0. That means the entire voltage of the third harmonic goes to 0. Poof, it's gone. With just one simple timing tweak, we have surgically removed the biggest piece of harmonic pollution from our output. And even better, by changing that angle alpha, we can also control the voltage of the fundamental, which gives us a way to dim the lights or slow down the motor. It's a huge step forward.
Now, the modified square wave is a really clever trick, but it's not perfect. It's great for killing one specific harmonic, but what about the fifth, the seventh, the 11th? To get a truly clean output, we need something much more sophisticated. And that brings us to the technique that is the absolute gold standard today, used in almost every modern high-performance inverter, pulse width modulation, or PWM. The idea behind PWM is both simple and totally brilliant. We start with two signals. The first is our reference wave. This is a perfect, low-frequency sine wave, and it's the beautiful output we're trying to create. The second signal is our carrier wave. This is a high-frequency triangle wave, and it's going to be the tool we use to build our reference. Then, we just continuously compare the two.
And the switching rule is dead simple. At any given instant, we just ask one question.
Is the voltage of our sine wave reference higher than the voltage of our triangle wave carrier? If the answer is yes, we tell the H-bridge to output positive DC voltage. If the answer is no, we tell it to output negative DC voltage. That is literally it. That's the entire logic. And this right here is the magic of PWM. The actual voltage coming out of the inverter isn't a smooth sine wave at all. It's this high-speed train of rectangular pulses, constantly flipping between full positive and full negative. But, and this is the whole trick, because we're switching so incredibly fast, the average value of all those little pulses perfectly traces out the shape of our sine wave reference. It's like we're sculpting a perfect sine wave out of thousands of tiny digital building blocks. And the best part? All those nasty low-frequency harmonics are gone. They've been pushed way, way up the frequency spectrum, all clustered around the high frequency of our triangle wave, where they're incredibly easy to filter out.
Now, to control this whole process, we have a couple of key dials we can turn. The first one is called the amplitude modulation ratio, which we just shortened to M sub A. This is simply the ratio of the height of our sine wave to the height of our triangle wave.
The easiest way to think about M sub A is that it's the master volume knob for the inverter. By making our reference sine wave taller or shorter compared to the fixed triangle wave, we can precisely control the voltage of the AC output we're creating. In fact, it's a perfectly linear relationship. The output voltage is just M sub A multiplied by our input DC voltage. It gives us precise, predictable control. Okay, so that's the volume control. The other key dial we have is the frequency modulation ratio, or M sub F. This is just the ratio of how fast our triangle wave is oscillating compared to how fast our sine wave is.
And if M sub A is our volume knob, then M sub F is our smoothness or resolution control. A higher M sub F means we're using more, much narrower pulses to build each cycle of our sine wave. Think of it like a higher pixel count on a TV screen. More pixels give you a smoother, cleaner image. Here, more pulses give you a smoother, cleaner output current. The trade-off, of course, is that switching faster means more energy losses in our transistors, which creates more heat. It can also create an audible high-pitched whine. So engineers always have to find that sweet spot between a perfect output waveform and overall system efficiency.
All right, so we've pretty much mastered the principles for creating a single, clean AC output. Now let's see how these same techniques get scaled up to run the massive three-phase motors that power our factories and connect huge renewable energy plants to the grid. So most big industrial motors don't run on the single-phase power you have at home. They need three-phase power for much smoother and more efficient operation. To create this, we basically just use 3 of our H-bridge legs side by side for a total of 6 switches. We apply the same PWM control to each leg, but we give each one a reference sine wave that's shifted by 120 degrees from the others. This creates 3 beautiful AC outputs that form a balanced 3-phase system. And here's a really fantastic bonus. In a balanced system like this, a whole group of harmonics called triplet harmonics, that's the 3rd, the 9th, the 15th, and so on, they just naturally cancel each other out. So we get an even cleaner output, basically for free. And when we get into really high-power, high-voltage applications, think grid-scale solar farms or connecting offshore wind turbines, engineers use an even more advanced design called a multilevel inverter. Instead of just switching between positive and negative DC, these devices use a clever combination of multiple DC sources to create a waveform that looks like a staircase. And as you can see, each of those steps gets it closer and closer to a perfect sine wave. This means you need much smaller, cheaper, and more efficient filters on the output, which is a huge deal at that scale.
So let's just take a quick step back and look at the journey we've been on. We started with a simple 4-switch H-bridge, the absolute core of the whole thing. We saw how its simplest output, the square wave, was just full of nasty harmonic noise. We then used Fourier analysis as our special lens to see and measure that noise. We learned a clever trick, the modified square wave, to surgically remove the worst offenders. And finally, we landed on pulse width modulation, the modern, elegant technique for sculpting almost perfect sine waves out of simple DC.
And that leaves us with one final thought to chew on. We've seen just how powerful PWM is, but is that the end of the story? What's the next step in this evolution? Could an even more advanced digital technique, something called space vector modulation, allow us to squeeze even more performance, even more efficiency out of these incredible devices? That's a topic for another deep dive, but it just goes to show you that the innovation in this field is always moving forward.
Hey, if you found this breakdown of inverters helpful, whether it's for your job, for your classes, or just out of curiosity, please consider subscribing to the channel and liking this explainer. It honestly helps us a ton in being able to create more content just like this. But even more important than that, our real goal here is to build a community. So if you have any questions at all about this topic, or if there's another complex subject you'd like to see us break down, maybe it's space vector modulation or something else entirely, please let us know in the comments below. I read every single one, and your feedback is what shapes what we tackle next. Thanks so much for watching.